Thank you for introduction, Nakazawa-sensei. So I'd like to talk about my project. So can you change the slide? Can you do that? Thank you. So I'm going to talk about our project on actuator allocation optimization for large degree of freedom field. I'm Taku NONOMURA, project manager, and from Nagoya University. So first of all, I'd like to show the summary of this project. So when you consider about the control of the weather, that we need to manipulate something like a heat, momentum, or phase transition. Any of these methods requires huge energy. So we need to significantly improve the effectiveness of these weather control interventions. In this project, we focus on the location of the intervention. So to enhance the effectiveness of the weather control, we need to organize, evaluate, and develop the optimization methods for actuator location. And if this research is gonna give us the indices where we need to give the heat source or water vapor. And we hope that this research leads to the successful weather control in future. So to achieve this goal, we form the research group like this. So team 1 is led by me, and that is the main part of this project. And team 2 is led by Professor Daisuke Tsubakino of Nagoya University, and that research is for the mathematical formulation. And team 3 is led by Junshi Ito of Taku University, and they conduct the research of the weather simulator that validates our method. So right-hand side shows the website, and we already have some organized session in international conference and domestic conference, and also some research group activity in the academic society in Japan. So then I would like to move to the outcome from the project. So far, we first focus on the research of the sensor optimization that can be used for the actuator location optimization as a dual problem. So we first developed 2 methods of the multi-objective greedy method and the randomized greedy method. These 2 methods accelerate the selection of the actuator so much. And also we evaluate the effect of the objective function when we select the sensors. All those information becomes the foundation of the research of the actuator optimization. So then we move to the research of the mathematical formulation. So this research was conducted by the Professor Daisuke Tsubakino. And first, we investigate relationship between the sensor optimization and actuator optimization, as shown in the table. And top row shows the sensor optimization problem, and the lower row shows the actuator optimization problems. Those 2 problems has a very strong relationship, and we can use sensor optimization algorithm directly to the actuator optimization problems. So this helps us to accelerate the research so much. And then we rigorously define the objective function of the actuator allocation optimization. So in this case, we propose to use a tangent linear model, and then we set the objective function as a maximization of the reachable set R. So that R is expressed by here matrix W. So this problem becomes the maximization of the matrix volume. And when we consider about a large degree of freedom problem like a fluid or weather, and in that case, we need to use a reduced order model as well. And finally, we discuss about the type and the magnitude order of the relation in the indices based on the evaluation method of the matrix volumes here, trace or largest eigenvalue or trace inverse determinant. All those guys are considered and discussed. So then I would like to move to the research of the actuator optimization. So this is the illustrative problem of the actuator optimization, we use the linearized Ginsburg-Landau model. So this is originally from the quantum dynamics, and but used as a toy model of the fluid dynamics. First, we discretize this equation in middle, and then we consider about the actuator optimization problem. So we have the delta function like input in the left-hand side bottom, and then we'd like to maximize the amplification at the terminal state. So this is the idea of this problem. Here we have the impulsive housing anywhere of the actuator, and then we'd like to maximize amplification here in the terminal state. So I would like to explain our algorithm with using this problem. So in this case, first we need to build up the reduced order model to calculate the sensitivity. So now we have the terminal state yt and the initial state y0. So we have the transfer function phi here. And this phi is modeled by the tangent linear model and the adjoint model. By repeating those tangent linear model and then the adjoint model and tangent model and then the adjoint model, finally we get the singular vectors. So by expressing the formulation here, terminal state can be expressed by those singular vectors, singular matrices, and then the initial states. So by obtaining this form, we can focus on this matrix here. So this guy is a right singular matrix, and also this is a sensitivity matrix. So by checking the distribution of this sensitivity matrix, then we can optimize actuator location. So concretely, we define the C matrix that is the actuator location matrix times the right singular matrix. So in this case, we maximize the CC transpose, determinant of the CC transpose, to get the most amplified actuators. So I would like to skip the more detail, but I would like to show the results of those optimized actuators. Left-hand side shows the optimized actuators, and then the right-hand side shows the random actuators. So this is the results. Then the optimized placement has a very large growth. On the other hand, random placement doesn't. So by using our algorithm, we can amplify actuator disturbances like this. Then we apply this algorithm to the several problems, including the fluid problem and also Lorentz 96. And I would like to point out one thing. And when we use this algorithm, we need adjoint equation. Yeah. So this is a right-hand side figure shows that the sensitivity distribution by calculating with adjoint model or without adjoint model. So red line shows the sensitivity calculated by without adjoint model. So it is noisy, and we cannot select actuator in this case. So we need to use the adjoint model based schemes. So finally, I'd like to move to the weather control problems. Okay. So we targeted the numerical simulation of the heavy rain in the western Japan from June 28 to July 8, 2018. So we consider about removing the water vapor of the actuator position at the ground. And the objective function, we set the minimization of the maximum precipitation. So for this simulation, we use a WRF plus that supports adjoint equation, as I told you. So the grid size is 10 kilometers. So before discussing the results of it, and I would like to show one more trick to speed up the calculation. So this is the implementation of the singular vector method, and the left-hand side shows the original singular vector method. We need the repetition of the tangent linear model, adjoint model, and tangent linear model, and the adjoint models. So it takes so long time to finish the calculation in world time clock. So on the other hand, we propose the randomized SVD method. In this case, we prepare m different pattern of the initial conditions and then we can calculate it simultaneously. And then we come back from the last state to the initial state by the adjoint equations simultaneously. So in this case, one round trip of the forward calculation and also adjoint calculation is good enough to obtain the singular vectors. So we use this method to accelerate the calculation. So then I would like to move to the results of this singular vector method. And this is the obtained response mode and the sensitivity mode. So unfortunately, there is no mode which simply increase or decrease the rainfall entirely. So we need to take care to use those modes to obtain the preferable results. So based on these modes, we can obtain the optimized sensor location and also optimize the actuators. Here, optimized sensors are located in these large precipitation regions. On the other hand, red triangle actuators locations are located upstream side, that is the southwest side of large precipitation regions. So this result seems promising and reasonable. So using those optimized actuator location, we try to control the maximum precipitation. So left two figures show the random placement, and please take care of the color bar, of the range of the color bar. That is very small. So these two doesn't affect the results so much. On the other hand, the proposed result has a significant effect on the precipitation. So right bottom show the maximum precipitation, and proposed methods can reduce the maximum precipitation so much. So the suboptimal placement achieves the smallest maximum precipitation. So on the other hand, we have the very large fluctuation rather than the other point with our target. So it is necessary to carefully consider the objective function from perspective of the minimizing damage caused by rainfall. So I would like to finish my presentation. So this is conclusion slide. So the actuator location optimization framework for efficient control of large-scale degree of freedom field, such as weather field, is proposed and validated. So next challenge is the more strongly nonlinear problem to optimize the actuator location. Thank you so much.